A faint shimmer spreads across the darkness, like the first flicker of a match in an endless night. It begins with silence, ancient, untouched, older than anything the human mind can truly grasp. Then, with a single command sent from millions of miles away, the James Webb Space Telescope opens its golden eyes. What it captures in that moment is not just light, not just dust, not just stars. It is a message from the other side of time, a whisper traveling across 13.5 billion years, carrying with it a secret the universe was never supposed to reveal. The image sharpens. Pixels arrange themselves into structures that defy logic. Clusters of galaxies, swirling, glowing, spiraling with elegance and chaos. Not one or two, not a handful, 200. 200 galaxies suspended in a cosmic cradle that should not exist. They appear fully formed, massive, mature, like ancient giants standing at the dawn of creation. Yet, according to everything science has taught us, these galaxies should not be here. They should not be possible. They are older than the universe is supposed to allow. Astronomers expected fog, dust, and the dim glow of infant stars. Instead, they found cosmic cities, organized, bright, structured, standing at a time when the universe was barely out of its violent birth. The moment these images were released, a chill ran through research labs around the world. Theories cracked. Models shuddered. For decades, scientists believed they understood the early universe, its timeline, its rules. But this scene, this impossible snapshot, struck like a revelation. The universe might have begun shaping itself far earlier, far faster, and far more mysteriously than anyone predicted. The light from these galaxies set out before Earth existed, before the sun had ignited, before atoms in your body had ever been forged. Across a universe still stretching, cooling, expanding into itself. It survived collisions, cosmic storms, gravitational distortions, the destruction of stars, the birth of others. And after billions of years of silent travel, it slipped into the JWST's mirror, a mirror engineered by human hands but aimed at something utterly beyond human comprehension. As researchers zoomed deeper into the data, unease grew into disbelief. These galaxies weren't gentle gatherings of baby stars. They were dense, heavy, mature. Some held more mass than the Milky Way would have at a much later stage in cosmic history. Their structures suggested complexity: spiral arms, bright cores, clusters of blazing stars. Features that, according to cosmology textbooks, should require hundreds of millions of years to appear. But this light came from a time when only tens of millions of years had passed since the Big Bang. In cosmic terms, it was as if you walked into a nursery and found fully grown adults speaking ancient languages. What force could have shaped them so fast? What unknown physics pushed matter to gather with such speed? What energy carved galaxies out of the darkness almost instantly after the universe began? These questions hang like ghosts over the discovery. Some scientists whisper that the standard model of cosmology may need rewriting. Others insist that unseen forces must have accelerated early formation. A few entertain possibilities that border on the unthinkable. New laws of physics, alternate cosmic histories, or hidden mechanisms that operated when time itself was still young and unstable. Imagine the scene. A universe freshly born from unimaginable heat, with space expanding faster than light, temperature plummeting, particles scattering wildly. In that turbulent chaos, the first stars should flicker hesitantly into existence. Yet the JWST reveals not hesitation, but confidence. An early universe that leaped forward, assembling entire galaxies as if it were racing against time. These galaxies glow like lanterns hung by an unseen architect, each one defying predictions, mocking expectations. The weight of this discovery is not merely scientific, it is existential. Humanity has always reached for the beginning, for a clue about where everything started and why anything exists. But when the universe answers with contradictions, with impossible structures from impossible eras, we are forced to confront a profound truth. Reality is far stranger than our equations dare admit. For now, the data is still being parsed, tested, challenged. But the image, those 200 galaxies, remains a wound in our understanding, a tear in the smooth fabric of cosmic logic. A reminder that the universe is not obligated to behave in ways that make sense to us. Somewhere out there, beyond all the light we can see, lie secrets older than the universe we think we know. The JWST has merely touched the surface, opened the first door, lit the first torch in a labyrinth older than time. And as the telescope continues to gaze deeper, farther, into realms untouched by human eyes, one question refuses to fade. If galaxies could form before the universe was ready for them, what else is waiting to be found in the darkness beyond? It began as a dream so ambitious, so fragile, that many believed it would never leave the drawing board. A telescope unlike anything humanity had ever dared to build, a machine designed not merely to observe the universe but to challenge it. The James Webb Space Telescope was conceived in conference rooms and laboratories, pieced together through decades of arguments, redesigns, failures, and stubborn persistence. Its purpose was simple in words yet impossible in scale: to see the universe as it was at the very beginning, to peer past the fog of cosmic infancy, to catch the first sparks of light ever born. But as its golden mirrors unfolded in the weightless silence of space, no one could have predicted that this machine would do more than observe history. It would threaten to rewrite it. Long before the telescope reached the stars, it lived as a blueprint, a concept whispered between scientists who wanted to build something capable of looking farther than any instrument in human history. Hubble had shown us galaxies glowing in ancient darkness, but its vision could only go so far. It was like trying to remember childhood through a fogged window. The earliest moments of the universe remained hidden behind walls of dust, time, and cosmic expansion that Hubble simply couldn't penetrate. To see beyond that boundary, something radical was required, something that could catch faint, stretched infrared light emitted billions of years ago. That idea grew into Webb. The challenges were monstrous. Webb would have to survive the coldest temperatures in space, operate at distances where no astronaut could repair it, and unfold flawlessly like an enormous mechanical flower in the vacuum of nothingness. A single mistake in any bolt, hinge, or sensor could doom the entire mission. Every engineer knew this. Every scientist feared it. Yet the project moved forward, driven by a collective hunger to see what lay beyond the cosmic horizon. They built mirrors polished to atomic precision, crafted from beryllium so light and strong they seemed unreal. They constructed a sun shield the size of a tennis court, layered like fragile petals that would protect the telescope from heat that could blind it. They assembled instruments so sensitive they could detect the warmth of a bumblebee on the moon. Then came the years of delays, cost overruns, redesigns, and political storms. Webb almost died a dozen times before it ever touched a rocket. Critics called it a fantasy. Supporters called it humanity's best hope of understanding where everything began. And through all the chaos, the telescope slowly took shape, piece by piece, wire by wire, mirror by mirror, until its golden hexagons gleamed like a crown forged for a cosmic king. On launch day, the world held its breath. As the rocket roared into the sky, scientists felt their hearts tremble. Webb was being hurled into a void where no rescue was possible. If it failed, decades of work would vanish in silence. But it did not fail. It soared, gliding across the black ocean of space until it reached its destination. Lagrange Point 2, a gravitational nest where it could drift in a delicate cosmic balance. And there, in absolute darkness, it began to awaken. One by one, its components unfolded with slow, deliberate grace. The sun shield stretched open like a silver sea. The mirrors tilted and aligned themselves with astonishing precision. The instruments cooled to near absolute zero, becoming capable of reading the faintest whispers of ancient photons. When the first calibration images arrived, scientists were stunned. Even the test patterns, simple star fields, were clearer, sharper, deeper than anything Hubble had ever seen. Webb was not just functioning. It was surpassing every expectation. Yet no one knew what was coming. No one expected that the telescope would tear holes in our understanding of the universe. The mission had been pitched as a quest to observe the first galaxies, but the assumption was simple. Those galaxies would be tiny, chaotic nurseries barely holding themselves together. Researchers imagined dim smudges, primitive structures, fragments of starlight suspended in a turbulent early universe. They thought they would see slow beginnings and cosmic infancy. But when Webb captured its first images of deep space, something shifted. The telescope returned not faint smears of newborn galaxies, but fully formed titans shining with impossible maturity. Their shapes were defined. Their brightness suggested star formation rates that defied physics. Their redshifts implied they existed at a time when the universe should still have been too young, too hot, too violent to form anything this complex. The moment scientists saw the data, silence filled the room. It was the kind of silence that follows a revelation, not a mistake. The realization spread quickly. Webb was not merely improving our view of the early universe. It was revealing a universe far stranger than the one we believed in. A universe where structure formed rapidly, aggressively, almost as if some unseen force had accelerated the birth of cosmic architecture. Webb was designed to confirm theories, to fine-tune our understanding of how galaxies grew. Instead, it was dismantling those theories piece by piece. But why did Webb see what others could not? The answer lies in its breathtaking design. Its infrared vision allowed it to pierce the cosmic veil and retrieve light that had been stretched across eons. Where Hubble saw darkness, Webb saw ancient signatures of creation. Where earlier telescopes glimpsed hints, Webb revealed entire structures. It was not just a tool, it was a revelation engine. The deeper Webb looked, the more unsettling the discoveries became. The telescope was built with the hope that it would help us understand the universe's first moments. Instead, it showed us that our understanding might be broken. The laws of cosmic evolution, once considered stable, now seemed fragile, incomplete. Every new dataset Webb returned created ripples of excitement and dread throughout the scientific community. Had we underestimated the power of early star formation? Was the timeline of the universe wrong? Or had we overlooked a fundamental force shaping the cosmos? In laboratories around the world, researchers began rewriting models, adjusting parameters, running simulations with frantic urgency. The universe they had spent their careers studying was slipping through their fingers like sand. Webb had become a mirror reflecting not only distant galaxies but the limits of human knowledge. As its instruments continued to scan the heavens, the telescope transformed from a dream into a disruptor, a machine that challenged every certainty we once held sacred. And yet, there was beauty in this disruption. Webb's golden mirrors, born from risk, sacrifice, and impossible engineering, were revealing a cosmos bursting with surprises. Every image was a reminder that the universe still holds secrets waiting to be uncovered. The telescope was built to break reality, to push the human mind into territory it had never dared to explore. And in doing so, it became more than a scientific instrument. It became a symbol of curiosity, courage, and the relentless human desire to understand the impossible. The universe does not speak in sound or motion. It speaks in light, ancient, fragile, stretched thin across the breadth of time. And long before the James Webb Space Telescope opened its mirrors, that light had already begun its journey, carrying with it stories older than every star we see today. It drifted through expanding space like a wandering ghost, dimming with every passing billion years. Its wavelengths pulled and stretched until they slipped beyond the visible spectrum. To most telescopes, this light was invisible, lost, forgotten. But JWST was crafted for this very purpose, to catch the oldest whispers the universe has ever sent. Imagine a photon, a particle of light, born in the fiery heart of a star that existed when the universe was still a cosmic infant. The temperature then was blistering. Matter was unsteady, colliding violently, forming the first atoms in a seething ocean of radiation. That photon burst free from its host star, beginning its long, lonely voyage. It slipped through dust clouds, dodged collapsing gas clusters, moved through regions of dark matter, and survived the gravitational pull of forming galaxies. As the universe expanded, the photon's wavelength stretched, turning redder and colder. What began as a bright spark eventually became a faint, elongated trace, an echo of creation moving through endless black. Billions of years later, that same photon struck the mirror of JWST. Its arrival was an impossibility made real, a survivor from the dawn of time, a tiny fragment of an era that should have been unreachable. And when enough of these ancient photons were collected, an image appeared, one that defied everything scientists thought they understood. To grasp why this is shocking, you must imagine the early universe not as a majestic cosmic panorama, but as chaos. After the Big Bang, the universe expanded with incredible speed. Space was dense, hot, and opaque. It took hundreds of thousands of years just for the first atoms to stabilize, and millions more for gravity to begin sculpting matter into clouds that could eventually ignite as the first stars. According to the Standard Model, galaxies should have taken even longer, hundreds of millions of years, to form into recognizable shapes. But the light captured by JWST tells a different story. The telescope's infrared sensors, cooled to temperatures near absolute zero, were designed to detect precisely this stretched ancient light. They could peer past cosmic dust, past intervening galaxies, past distortions in the fabric of spacetime. When JWST's first deep-field images came in, astronomers expected faint smudges representing the earliest moments of cosmic dawn. But instead, they found something that shook the foundations of cosmology. Clearly defined galaxies, some bright, some massive, some packed with stars far too mature for the era they came from. How could such structures exist so early? The light from these galaxies showed extreme redshift, a stretching so dramatic that it placed their origin at a time when the universe was only a few tens of millions of years old. Light traveling across 13.5 billion years should have revealed chaos and primal turbulence. But instead, JWST revealed organized cosmic architecture. It was like opening a time capsule expecting baby footprints, only to find fully grown human footprints instead. The more astronomers studied the redshift signatures, the more unsettling the discoveries became. Redshift is supposed to act as a cosmic clock. The higher the redshift, the earlier the galaxy. But these numbers didn't make sense. They pointed to galaxies that formed before the timeline allowed formation. That meant one of two things: the measurements were wrong, or the universe was behaving differently than believed. But JWST's instruments were too precise for the first explanation to stand for long. Every new dataset reinforced the same impossible truth. These galaxies were real, fully formed, and ancient beyond reason. Scientists found themselves struggling with a contradiction that felt almost poetic. The farther JWST looked, the less sense the universe made. To understand why this is so destabilizing, consider what redshift really represents. As the universe expands, the space between galaxies stretches. Light traveling through this stretching space becomes elongated, shifted into the red part of the spectrum. The greater the redshift, the farther away, and thus the older the source. JWST didn't just detect slightly higher redshifts than expected. It detected galaxies whose redshifts placed them absurdly close to the Big Bang itself. The light from these galaxies doesn't just describe early structure, it challenges the very timeline of the cosmos. Picture the early universe as a dark ocean, newly born and still swirling with violent energy. Gravity was only beginning its work. Hydrogen gas was gathering into clumps, cool enough to collapse into the first stars. This process should have taken time, slow, gradual, predictable. But JWST shows a universe that acted with urgency, forming massive galaxies at speeds that break current cosmological models. Each photon arriving at JWST from that era is a contradiction. It is a witness to an event that should not have been possible. These photons paint an image of cosmic cities glowing brightly at a time when the universe should barely have had the ingredients to build a single star. The deeper scientists look, the more mystery they uncover. Some galaxies appear too bright, too dense, too heavy. Others contain star populations that seem improbably old. A few look rotationally stable, as if shaped by processes that require hundreds of millions of years, yet their light says otherwise. It's as if time in the early universe passed differently, or matter behaved in ways we haven't yet understood. What makes this even more unsettling is that the data comes not from a single observation, but from multiple independent surveys. Different teams, different tools, different conditions, yet the same impossible results. The early universe wasn't empty and slow. It was bustling, creative, productive. It was building galaxies with a speed and intensity that defy every known rule of cosmic evolution. In the dim glow of those ancient galaxies, one can almost feel the tension. The universe trying to tell us something, whispering through stretched wavelengths and fragmented light. JWST was designed to peer into darkness, but what it found was illumination, an illumination that exposes the cracks in our understanding. Each photon that struck the telescope's golden mirrors carried a message from a time before planets, before elements, before the cosmic web had woven itself into the vast structure we see today. These photons were not simply particles of light. They were historical artifacts, remnants of a universe that seemed to grow faster and more mysteriously than any textbook predicted. And as JWST continues to collect this ancient light, a deeper question emerges. If the first galaxies formed so quickly, what force pushed them into existence? What unknown process shaped the earliest structures with such confidence and speed? And most importantly, what else might be hidden in light that has not yet reached us? With every photon captured, the universe reveals a little more of itself, and with every revelation, the mystery only deepens. The deeper the James Webb Space Telescope peers into the vastness of the cosmos, the more it becomes clear that the universe is not a static, predictable place, but a dynamic, ever-changing landscape of wonder, chaos, and mystery. In the violent ballet of colliding galaxies, where stars are flung across space, gas clouds collide with explosive energy, and dust lanes stretch like cosmic rivers, a subtle yet profoundly enigmatic presence has emerged. This is the anomaly, a faint, elusive object suspended between the two massive galaxies, whose quiet glow and shifting patterns resist all conventional classification. Unlike the surrounding chaos, which obeys the gravitational and physical laws scientists have meticulously mapped, this anomaly behaves in ways that defy expectation. Infrared imaging reveals intricate filaments of light weaving through the darkness, delicate structures that pulse faintly and irregularly, almost as if the object were alive. Spectral analysis adds another layer of intrigue. Its energy signatures do not correspond neatly to any known type of matter or radiation, hinting at physics that may be entirely new or poorly understood. The anomaly stands as both a scientific challenge and a cinematic marvel, a quiet counterpoint to the violent brilliance of the colliding galaxies surrounding it. Cinematic visualization amplifies this contrast, transforming abstract astrophysical phenomena into a story the mind can see and feel. The galaxies themselves are ablaze with activity. Clouds of gas collide with explosive force, igniting stellar nurseries that flare in electric blues, deep reds, and soft golds. Supermassive black holes at the galactic centers emit energetic jets that pierce the interstellar medium, their light stretching across millions of light-years. Spiral arms twist and stretch under tidal forces, creating streams of stars that arc outward like glowing ribbons in a cosmic storm. Against this backdrop of violent motion, the anomaly hovers silently, almost defiantly, a subtle, ghostly presence that draws the eye and the imagination. The juxtaposition of chaos and calm is cinematic perfection, reinforcing the central tension of the narrative. In a universe of immense energy and predictable physical laws, something exists that operates outside them, challenging our understanding and captivating our curiosity. Scientists studying the anomaly are both exhilarated and cautious. Every faint flicker, every subtle variation in brightness, every irregularity in spectral data becomes a piece of an immense puzzle. Rigorous observation is combined with imaginative speculation as researchers attempt to discern its nature. Advanced simulations factor in the gravitational dynamics of the colliding galaxies, the density and movement of interstellar gas, the influence of dark matter, and even the potential role of high-energy phenomena near supermassive black holes. Yet the anomaly refuses to conform to these models. Each simulation highlights the limitations of current understanding, revealing gaps in knowledge and suggesting the possibility of physical processes that have never before been observed. This scientific tension mirrors the cinematic tension. The audience feels both awe at the grandeur of the galaxies and unease at the anomaly's inscrutable behavior. Hypotheses regarding the anomaly's nature are numerous and bold. Some researchers suggest it could be a nascent black hole, forming quietly amid the turbulent space between the galaxies, drawing in gas and dust while remaining largely invisible except for subtle gravitational and infrared effects. Others propose it may be a dense pocket of exotic matter, a form of substance that interacts weakly with ordinary matter and light, detectable only through subtle energy fluctuations. Another possibility is that it is a transient phenomenon, visible only during this particular phase of the galactic collision, appearing as a brief window into processes that occur on a timescale of millions of years, ephemeral yet monumental. Each hypothesis carries profound implications. The discovery of exotic matter would rewrite our understanding of the universe's composition. A transient anomaly would highlight the fleeting nature of cosmic events. A nascent black hole would provide a rare glimpse into the earliest stages of galactic evolution. The narrative tension of discovery is heightened by the fact that none of these explanations fully accounts for the anomaly's observed behavior, keeping scientists and viewers alike on the edge of understanding. Beyond the scientific intrigue lies a profound philosophical and emotional dimension. Observing an object that defies comprehension forces both researchers and viewers to confront the limits of human knowledge. For millennia, humanity has sought to map, measure, and understand the heavens, believing that the universe is orderly and knowable. Yet the anomaly challenges this notion, suggesting that even amid the precision of physical law, there exist phenomena that elude categorization. Its quiet, persistent presence amid galactic chaos becomes a symbol of the unknown, evoking wonder, humility, and a sense of cosmic scale that is difficult to fully grasp. Cinematically, this is expressed through contrasts. Violent, chaotic star formation and tidal distortions surround the anomaly, while its subtle glow remains steady, almost imperceptible, inviting contemplation and reflection. The audience is drawn not just into the mechanics of galactic collision, but into the deeper emotional experience of facing something truly alien and unknowable. The anomaly's behavior over time adds yet another layer of complexity. Observations across months and years reveal slight pulsations, subtle shifts in position, and variations in energy emission. These patterns suggest a dynamic process at work, something that evolves on a timescale far longer than human observation, yet measurable through the patient accumulation of data. Researchers meticulously track these changes, analyzing light curves, spectral data, and infrared images. Sophisticated algorithms filter out noise, cosmic interference, and instrumental artifacts to isolate the anomaly's true behavior. The universe, as we understand it, has a timeline, a carefully constructed sequence of events that unfolds from the chaos of the Big Bang to the structured cosmos we see today. For decades, this timeline has been a cornerstone of modern cosmology, built on equations, observations, and countless simulations. It told a story that felt solid, predictable, logical. But when the James Webb Space Telescope revealed galaxies that existed far earlier than theory allowed, that timeline began to crack, sending fractures through the foundation of everything we believed about cosmic evolution. To grasp the magnitude of the crisis, imagine the early universe as a vast field of glowing embers left behind by an unimaginable explosion. For hundreds of thousands of years, the cosmos was an opaque fog, so dense with photons that light could not travel freely. Only after this fog cooled did atoms form, leading eventually to the birth of the first stars. These stars were expected to ignite slowly, cautiously, like the first sparks catching fire in cold wood. Galaxies were supposed to emerge even later, forming gradually from clumps of gas pulled together by gravity over tens to hundreds of millions of years. But the galaxies revealed by JWST were not the slow-built structures of this established timeline. They were massive, bright, mature, and clustered, conditions that theory said should require immense stretches of time to develop. Their existence implied that something in the story of the universe was missing or misaligned. Something about how time operated in the beginning might not match our assumptions. In classrooms and textbooks, diagrams of the early universe show a neat path. The Big Bang at one end, the cosmic microwave background a bit later, the dark ages in between, and finally the ignition of the first stars in a long, delicate process. But the sight of ancient, fully formed galaxies compressed into the universe's earliest epoch is like finding skyscrapers standing tall in the middle of a world still molten and forming volcanoes. It doesn't just challenge the timeline, it destroys it, Scientists began revisiting the models that predicted how quickly matter could clump together. Gravity, they knew, acts slowly on cosmic scales. Even in regions where matter was denser than average, it should take hundreds of millions of years for enough gas to gather into the massive structures JWST observed. Yet here were galaxies with the mass of billions of suns, assembled in a cosmic heartbeat. Their stars burned hot, fast, and bright, signaling rapid, almost frantic formation in an era where the universe should still have been cooling from its explosive birth. The contradiction grew sharper with each analysis. These galaxies weren't mere outliers or statistical anomalies. They were frequent, numerous, and consistent across different JWST observations. That meant the accepted timeline wasn't just slightly off, it might be fundamentally flawed. Some scientists proposed that the universe might have condensed matter more efficiently early on, perhaps because the distribution of dark matter was different from what simulations predict. Others speculated about exotic physics, unknown forces or particles that accelerated early structure formation. A few even suggested that time itself may have flowed differently in the universe's infancy, stretching or compressing in ways that conventional cosmology couldn't account for. The idea sounds strange, but in physics, time is not a rigid, universal tick-tock. It bends, stretches, and warps around mass and energy. If the early universe had conditions we still do not understand, it's possible that time behaved in ways that changed the pace of cosmic evolution. A process that seems impossible in our timeline might have been perfectly natural under different temporal rules. Still, such explanations only raised more questions. If time flowed differently, what dictated its rhythm? If dark matter behaved unusually, why did it stop doing so later? If unknown forces drove early formation, why did they vanish? The more scientists tried to repair the cracks in the timeline, the wider those cracks grew. The crisis deepened when JWST detected galaxies with chemical signatures suggesting generations of stars had already lived and died by the time their light was emitted. This implied not just early star formation, but rapid recycling of stellar material, a process that normally takes vast stretches of time. The presence of heavier elements in such ancient galaxies was like discovering ruins of an advanced civilization in a world still dominated by primordial landscapes. How could so much stellar evolution have occurred in such a short span? Every unexplained detail pointed back to the same unsettling truth. The universe was far busier, far faster, far more productive in its earliest stages than anyone expected. The timeline could no longer hold. Researchers attempted to adjust their models, shifting the start of star formation earlier, pushing galaxy formation closer to the Big Bang. But each adjustment conflicted with fundamental physics. You can't simply move events backward without rewriting the conditions that made those events possible. And if you rewrite those conditions, you inevitably rewrite the laws governing them. This is the heart of the crisis. Any attempt to fix the timeline leads to deeper inconsistencies. It's like tugging on a single loose thread in a sweater, only to watch the entire garment unravel. As astronomers debated the implications, a quiet unease began to spread. What if the timeline we built wasn't a timeline at all, but an approximation shaped by limited data? What if the universe's true history is stranger and less linear than we imagined? What if the early cosmos had phases or dynamics that our current theories can't yet capture? This unease grew when multiple observations pointed to similar anomalies in different parts of the sky. These weren't isolated discoveries. They were widespread, systematic, telling a coherent but disturbing story. The early universe wasn't slow, gentle, or patient. It was fast, efficient, and radically creative. Even the cosmic microwave background, the oldest light we can observe, came under renewed scrutiny. Some researchers wondered if subtle irregularities had been overlooked, masked by noise, or misunderstood. Others speculated that inflation, the rapid expansion that occurred moments after the Big Bang, might have been more chaotic or extreme than previously theorized. If inflation behaved differently, the entire sequence of cosmic events could have unfolded in unexpected ways. The cracks in the timeline now resemble fractures spreading across a frozen lake. Each crack hints at underlying weakness. Each fracture points to a deeper truth that lies beneath the surface. And with every new JWST discovery, the ice groans louder. What if this is only the beginning? What if the timeline isn't broken, but incomplete? What if the universe has been hiding entire chapters of its early history? Chapters we are only now beginning to uncover. The answers remain uncertain. But one thing is clear. The discovery of the first 200 galaxies has forced humanity to confront a possibility that once seemed unthinkable, that the universe did not evolve according to the rules we thought it followed. It may have taken shortcuts, operated under unfamiliar laws, or expanded through phases we never imagined. In the cracks of the cosmic timeline, the universe is revealing its true story. A story far stranger, faster, and more mysterious than any we have told before. The early universe was a place of violence, heat, and unrestrained chaos. Space itself was raw, still trembling from the force of its own birth. Gas clouds swirled like restless storms, dark matter pooled in invisible rivers, and gravity began pulling the scattered debris of creation into clumps. From this turbulence, the first stars were expected to emerge slowly, small flickers of light building themselves up over time. But what the James Webb Space Telescope revealed shattered that gentle expectation. The stars in those ancient galaxies were not delicate sparks. They were monsters. To understand the scale of this revelation, imagine a star so massive that its core burns at unimaginable temperatures, fusing elements with a ferocity that makes ordinary stars look like dying candles. These colossal giants, known as population 3 stars, are believed to be the universe's very first generation of stars. They formed from pristine hydrogen and helium, born in a cosmos untouched by heavier elements. According to theory, they lived fast and died young, exploding in titanic supernovae that seeded the universe with the raw ingredients of planets, moons, and life. But even these theoretical giants were expected to be rare and difficult to detect. They were supposed to appear as isolated beacons in the darkness, struggling to form in a universe not yet ready to support such intense creation. What JWST found instead was a cosmic landscape filled with the fingerprints of these monstrous stars. Entire galaxies seemed to be powered by them, galaxies that were too bright, too hot, too massive to be explained by ordinary stellar populations. The light they emitted was harsh and energetic, the kind produced only by stars many times larger than our sun, sometimes hundreds of times larger. These stars burned with the intensity of cosmic furnaces, pushing out radiation strong enough to reshape their surroundings. The implication was staggering. Perhaps the early universe was dominated by these colossal stars, forming at a pace and scale that defied every model of star formation. Instead of a slow cosmic dawn, there may have been an explosion of supermassive starlight, igniting the cosmos like a sudden celestial wildfire. Scientists began to imagine scenes that felt almost mythic. Enormous blue-white stars rising out of the cosmic fog, their surfaces boiling with nuclear fury, their light piercing the darkness in sharp, violent rays. Their lifespans measured not in billions of years, but in mere millions, cosmic mayflies burning out almost as soon as they were born. When they died, they didn't simply fade. They detonated, tearing themselves apart in supernovae that rivaled small galaxies in brightness, blasting heavy elements into the void. If such stars were common, it would explain the impossible brightness of the early galaxies. A single massive star could outshine thousands of smaller ones. Multiply that by thousands of such stars, and the early cosmos becomes a realm of overwhelming radiance. But that raised a new, unsettling question. How did these giant stars form so quickly? To create such monsters, gas clouds must collapse with incredible efficiency. But the early universe should have been too unstable for that. The temperature was too high, the matter too sparse, the gravitational structures too undeveloped. Yet the evidence pointed to rapid, large-scale collapse, huge reservoirs of primordial gas gathering themselves into stars that dwarfed anything seen in the modern universe. One theory suggested that dark matter, which makes up most of the universe's mass, might have played a more aggressive role in those early years. Perhaps dark matter clumped so effectively that it created gravitational traps, regions where gas pooled rapidly, forming massive stars almost instantly. These dark matter cradles would have accelerated star formation far beyond what normal matter could achieve alone. Another theory ventured even deeper into the bizarre. Maybe the physics of the early universe favored the creation of massive stars. The cosmic environment may have been tuned in a strange, unknown way. Perhaps temperatures, densities, or even the fundamental constants behaved differently during the universe's first moments. But even these ideas could not fully explain the sheer number and intensity of early stars implied by the JWST observations. Some of the distant galaxies appeared to have undergone multiple generations of massive stars in rapid succession. That meant the first stars formed, lived, died, and seeded new stars at speeds far beyond anything theorized. The timeline simply didn't allow for this level of stellar turnover. The mystery deepened with each new observation. Some galaxies showed signs of intense radiation fields, radiation so strong that it stripped electrons from atoms across vast distances. This kind of ionizing power could only have come from extremely hot, massive stars. Others exhibited chemical signatures suggesting that heavy elements, iron, carbon, oxygen, had already been forged and scattered throughout the galaxy. But these elements require multiple cycles of star birth and death. How could such cycles have occurred in such a short span of time? It was as if the early universe had skipped the slow learning phase and plunged straight into chaos-driven creativity, forming stars of impossible size and abundance. And somewhere in that frenzy, the first galaxies arose, shaped by these stellar beasts like sculptures molded by fire. To visualize these cosmic monsters, imagine a star so enormous that it would swallow our solar system whole, its surface hotter than 1,000,000 suns combined. Its core churns violently, fusing hydrogen into helium at a rate that makes ordinary stars look gentle. Its radiation pushes against surrounding gas with such force that it sculpts the galaxy around it, carving tunnels, rings, and glowing shells of energized matter. When it collapses, it does so with explosive power, sending shockwaves through the young galaxy and triggering the birth of new stars. If the early cosmos was filled with such giants, the first galaxies were not quiet nurseries. They were war zones of light and fire. Star formation wasn't a gentle glow. It was a frenzy, a cosmic storm, an inferno that built galaxies through destruction as much as creation. Yet even with such chaotic power, something still didn't add up. These monstrous stars could explain some of the brightness and mass of the early galaxies, but not all. They could accelerate star formation, but not enough to account for galaxies that seemed fully mature. They could reshape their surroundings, but not fast enough to create ordered structures in so little time. It was a partial answer, a clue, a piece of the puzzle, but not the full picture. The possibility remained that even these colossal stars were not enough. The universe, in its earliest heartbeat, seemed to operate under rules we do not yet understand. These cosmic monsters may have lit the path, but they did not solve the mystery. Instead, they opened a deeper one. If the first stars were monsters, what created the monsters? Long before galaxies took shape, before stars ignited, before atoms found stable forms, something violent happened in the first fractions of a second after the universe began. A moment so brief it cannot be measured by ordinary time. A moment so explosive that every galaxy, every star, every particle of matter was shaped by its echo. This moment was cosmic inflation, the sudden, faster-than-light expansion that stretched the newborn universe from the size of a subatomic particle to something unimaginably vast. For decades, inflation was treated as a mathematical necessity, a solution that cleaned up the messiness of the early cosmos. It made the equations work. It smoothed out the universe. It explained why distant regions of space look similar. But JWST's discovery of impossibly early galaxies has pushed inflation back into the spotlight, and this time it is not a neat solution. It is a suspect. Inflation was always strange. It required the universe to expand at speeds that defy comprehension, many orders of magnitude faster than the speed of light. It demanded an unseen field, the inflaton, to trigger this runaway stretching. It suggested that reality itself ballooned outward like a soap bubble blown too fast to follow. Once inflation stopped, the universe continued to expand more slowly, like a pulse easing after a violent heartbeat. That violent heartbeat, cosmologists believed, set the stage for everything that followed. But what if inflation did more than stretch space? What if it sculpted the universe with chaotic bursts, uneven surges, hidden seams of concentrated energy. If inflation was not smooth and gentle, but turbulent, unpredictable, unstable, then the earliest galaxies might not be anomalies. Instead, they might be fossils of a deeper instability imprinted into spacetime itself. Imagine inflation not as a single explosion, but as waves of uneven expansion rippling across the newborn universe. In some regions, space might have expanded frantically, thinning out matter until it nearly vanished. In other regions, dense pockets left behind by inflation's uneven retreat, matter could have clumped together violently, collapsing under its own weight almost instantly. These dense pockets could have served as the seeds for the monstrous galaxies JWST now sees, forming cosmic structures earlier and faster than any current model predicts. The idea sounds extreme, but the early universe was a place where extremes were the norm. Temperatures were trillions of degrees. Energies were so high that known physics trembled at the edge of failure. The fundamental forces themselves, gravity, electromagnetism, the strong and weak nuclear forces, were still separating, like hot metals cooling from a molten blend. If inflation flickered, stalled, or surged unpredictably during these transitions, small fluctuations could have grown into massive structures with incredible speed. Scientists have long known that inflation leaves fingerprints, temperature variations in the cosmic microwave background. These variations are tiny, 1 part in 100,000, but they map the earliest density ripples in the universe. Yet these ripples predict slow, orderly formation of galaxies. What JWST has revealed is not slow or orderly. It is explosive, accelerated, aggressive. Some physicists began to suspect that inflation may have amplified certain density fluctuations far more strongly than models assumed. If some regions were boosted in density by even a small percentage during inflation, they could have collapsed into stars and galaxies almost immediately. These overdense regions would have acted like gravitational wells, pulling matter inward at a speed that defied expectations. Others proposed that inflation didn't end cleanly. Perhaps it sputtered, shutting off in some regions before others. This uneven ending would create cosmic domains, zones where matter was more concentrated, where gravity gained the upper hand earlier, where galaxies could form in defiance of the expected timeline. Such domains would be invisible today, their boundaries long stretched beyond recognition. But their legacy would remain in the form of early, impossible galaxies scattered across the universe. More radical theories emerged too, ideas once tucked away at the edges of scientific speculation. Maybe inflation wasn't a one-time event but part of a more complicated cosmic behavior, with secondary bursts or local fluctuations. Perhaps the inflaton field itself was unstable, flickering like a faulty engine, leaving behind gravitational scars where matter could gather at unprecedented rates. Some even suggested that inflation might have produced exotic forms of matter that later decayed, dumping energy into certain regions and accelerating star formation. But these explanations carried a darker implication. If inflation behaved unpredictably, then the universe is not the smooth, balanced cosmos we imagine. It is a patchwork stitched together by violent expansion, shaped by randomness at a scale too large to truly comprehend. The early galaxies revealed by JWST might be symbols of this cosmic patchwork, evidence of a universe far less uniform than we believed. Still, not everyone was convinced that inflation alone could explain the anomalies. Some pointed out that inflation, as currently understood, cannot simply generate fully formed galaxies. It might create density variations, but the timelines still seem too short. Could inflation really have produced gravitational cradles so powerful that entire galaxies emerged almost instantly? As the debate intensified, one unsettling possibility began to surface. Inflation may not merely be insufficient, it might be wrong. For decades, inflation has been considered the best explanation for the universe's uniformity. But alternate theories exist. Some propose that the universe had a pre-Big Bang phase, a contracting era that left imprints on the cosmos. Others suggest that spacetime itself may have quantum fluctuations that shaped early structure. Still others propose that inflation might be only one manifestation of a deeper, unknown process, something that drives cosmic expansion in ways we have not yet discovered. The presence of galaxies that should not exist acts like a spotlight, forcing scientists to confront the possibility that inflation, as elegant as it sounds in textbooks, might be oversimplified. The early universe may have been governed by physics we cannot yet test, cannot yet observe, cannot yet simulate. A realm where the rules as we know them bend, stretch, or dissolve entirely. And yet, there is beauty in this uncertainty. Inflation, even as a flawed suspect, opens a breathtaking window into the universe's first heartbeat. It invites us to imagine a cosmos ruled by shifting forces, where matter forms and reforms in patterns beyond human intuition. It challenges us to rethink the beginning, not as a clean explosion, but as a wild, unpredictable birth. When JWST captured those early galaxies, it didn't just reveal ancient light. It triggered a crisis that reaches into the foundations of cosmology. Inflation, the theory once thought to tame the chaos of the Big Bang, now stands on trial. Its neat, orderly picture of the early universe no longer matches the evidence. Long before stars were born, before galaxies spiraled into existence, before light carved its first lines across the darkness, there was something else already present. Something silent, invisible, and overwhelmingly dominant. Dark matter. It neither glows nor reflects, neither burns nor cools. Yet it shapes everything. It is the hidden architecture of the cosmos, the unseen skeleton upon which the universe builds its grandest structures. And now, in the face of JWST's shocking discoveries, dark matter has emerged as one of the most compelling suspects behind the impossibly early galaxies. Because if ordinary matter couldn't have formed galaxies so quickly, perhaps something hidden helped sculpt them long before the universe should have been ready. Imagine the earliest universe as a swirling sea of particles, chaos barely tamed by expanding space. Hydrogen and helium drifted freely, unable to collapse into stars without enough time or gravitational pressure. But dark matter, whatever it is, was already gathering, pooling into massive, invisible halos. These halos were like wells carved into the fabric of spacetime, deep depressions that ordinary matter could fall into. Cosmologists have long believed that these halos acted as cradles for future galaxies. But JWST suggests something far more dramatic. Dark matter may have begun building these cradles almost instantly. To visualize this, imagine throwing pebbles into a calm lake. Ripples spread slowly, gently. But now imagine tossing mountains instead of pebbles. The lake churns violently, sending waves crashing in every direction. That is the difference between ordinary matter and dark matter in the early universe. Dark matter was the mountain, a gravitational force so intense that it could shape regions of space even before atoms had stabilized. And if those dark matter halos formed far earlier than expected, they could have acted as cosmic traps, snaring gas clouds and compressing them into stars at terrifying speed. When JWST revealed bright, massive galaxies appearing just a few tens of millions of years after the Big Bang, many scientists turned their attention to the invisible. Could dark matter halos have been far denser in the early universe? Could they have collapsed faster, forming deep gravitational wells that pulled ordinary matter inward like a tidal wave? The idea is bold but not impossible. If dark matter gathered into structures only a fraction earlier than predicted, it could explain how stars formed so quickly, how galaxies grew so large, and why the early universe seemed so unnaturally productive. But the evidence goes deeper. Some of the ancient galaxies JWST detected are too small in physical size yet too heavy in mass, an odd combination that suggests they were tightly compressed by something stronger than their visible matter alone. Their rotational speeds are also unusually high for such early epochs. Fast rotation usually requires massive halos of unseen material. The simplest explanation is that dark matter dominated these galaxies' formation from the very beginning, shaping them with an invisible hand. Scientists describe dark matter as a cosmic scaffolding. It does not build the structure itself, but everything else attaches to it. But what if, in the early universe, dark matter was doing more than scaffolding? What if it was actively directing the first formation of galaxies, guiding matter into place before physics says it should have been possible? Some models propose that dark matter may have cooled faster in the early universe than ordinary matter. If true, it would have allowed dark matter to clump earlier, collapse earlier, and form gravitational structures earlier. These structures, dense halos, could then drag ordinary matter toward their centers, forcing gas to collapse with speed that defies current understanding. In such an environment, massive stars could form in bursts, lighting up the halos like cosmic firestorms. Others think dark matter might have had more exotic interactions in the earliest moments of time. Perhaps dark matter particles collided with one another or behaved like fluids, forming dense cores that rapidly seeded galaxy formation. Today, dark matter seems cold, slow, largely inactive. But in the early universe, under unimaginable temperatures and pressures, it may have behaved differently, transitioning from a fluid-like phase to a stable one. If such a phase transition occurred, it might have created exceptionally dense regions that pulled ordinary matter inward with overwhelming gravity. This idea gains weight from a specific subset of mysterious early galaxies, those showing signs of possible dark matter dominance even before significant star formation began. Their structures appear unusually compact, as if gravity forced them into tight forms before internal processes had time to expand them. Such galaxies, if confirmed, could be the smoking gun, direct evidence that dark matter played a more aggressive role than anyone anticipated. But dark matter's hidden hand also raises disturbing questions. If dark matter shaped the early universe so efficiently, why did it slow down? Why does the modern universe seem more balanced, more gradual, more predictable? Perhaps conditions in the early universe allowed dark matter to behave in ways it no longer can. Perhaps dark matter cooled, stabilized, and became more passive as cosmic expansion diluted its density. Or perhaps the early universe was simply different, a realm governed by laws we no longer experience. Some theorists even propose that dark matter may come in multiple forms. Maybe early dark matter was more interactive, more dynamic, more capable of forming clumps rapidly. Over time, only the stable, non-interacting form remained. If so, the early universe may have been filled with dark matter behavior we can no longer detect or replicate. Another possibility emerges from simulations. Dark matter halos might have formed in a cascading pattern, large halos collapsing first, followed by smaller ones. This is the opposite of what standard cosmology predicts. If large halos formed earlier, they could have hosted massive galaxies almost instantly. For generations, humanity has lived with a quiet confidence, an unspoken belief that the universe is governed by rules we understand. Gravity pulls, matter collapses, stars ignite, galaxies form, time flows forward. These principles, tested and refined, built the pillars of modern cosmology. Yet when JWST revealed galaxies that should not exist, forming at a pace and scale beyond the limits of known physics, that confidence cracked. Suddenly, the familiar rules seemed fragile, incomplete, perhaps even illusions. And in the wake of this cosmic shock came a whisper, a disturbing thought shared only in the dim corners of research labs and late-night discussions among physicists. Maybe the laws of physics in the early universe were not the laws we know now. This thought is not comforting. It is unsettling, exhilarating, terrifying all at once. Because if the early universe played by different rules, then everything we understand, our equations, our constants, our theories, are only approximations of a deeper, hidden reality. Imagine standing in a vast hall whose walls shift every time you turn away. You think you know its shape, but each time you look back, it has changed. That is what the universe feels like now. What JWST uncovered threatens the idea of stability in the laws that govern cosmic evolution. Some physicists began to ask whether the fundamental constants, numbers woven into the fabric of physics, might have been different in the universe's infancy. The speed of light, the strength of gravity, the behavior of quantum fields. These are usually treated as sacred, immutable. But what if they were still settling during the universe's earliest moments? What if gravity was stronger, pulling matter together with an urgency we cannot imagine today? Or what if some unknown force filled the early cosmos, pressing matter into stars and galaxies before the universe had time to breathe? There are hints, small, strange, uncomfortable hints, that this might be true. A few of the earliest galaxies revealed by JWST shine with an intensity that suggests star formation far more efficient than any modern process. Their stars seem heavier, older, more massive. Their structures appear stable in ways that conflict with the violent turbulence expected at the dawn of time. It is as though the early universe allowed matter to take shortcuts, forming complex systems without the long, delicate steps required today. But shortcuts imply rules bent or broken. One of the most provocative ideas suggests that quantum mechanics may have behaved differently in the universe's earliest moments. Normally, quantum fluctuations appear and vanish little by little. But in the extreme energy of the newborn universe, these fluctuations may have expanded catastrophically, creating sudden pockets of high density, cosmic seeds much larger than expected. These seeds could collapse into galaxies almost instantly, bypassing the slow buildup predicted by standard physics. Another hypothesis centers on gravity itself. Einstein's equations describe gravity as the curvature of spacetime, but those equations may not hold perfectly under the extreme pressures of the early cosmos. Some theorists suggest that gravity could have acted with greater strength or behaved nonlinearly, compressing matter in ways we would never see today. Under such conditions, galaxies would not need hundreds of millions of years to form. They might arise in mere thousands. Then there is the unsettling possibility that dark energy, the mysterious force accelerating cosmic expansion, may once have behaved differently as well. Perhaps it fluctuated wildly, pushing and pulling space in unpredictable rhythms. These fluctuations could have driven matter together instead of apart, creating natural pathways for early galaxy formation. In such a universe, stability would be a fleeting illusion, and structure could emerge not from calm order, but from violent bursts of energy. But the most haunting idea is this: the laws we consider fundamental may not be fundamental at all. They may be emergent, rules that crystallized gradually as the universe cooled, like ice forming patterns on a frozen lake. Before those patterns solidified, physics may have flowed freely, shifting between states we cannot yet imagine. In that early, fluid-like realm, matter might have obeyed strange rules, interacting through forces that no longer exist, assembling structures that modern physics deems impossible. It is a sobering thought. The early universe might have been a laboratory of exotic physics, governed by conditions that evaporated long before the first galaxies matured. JWST may be showing us fossils of an era where reality itself was unstable, where matter behaved like a creature learning to walk, unpredictably, chaotically, and faster than it ever would again. Yet even as these ideas spark excitement, they also evoke a quiet, creeping dread. Because if the laws of physics evolved over time, then our understanding of the universe becomes a story with missing chapters. We have built theories on the assumption that the rules were the same from the beginning. JWST's discoveries suggest that the beginning may have been governed by a different script entirely. Some researchers fear that we may never fully understand those early conditions. The clues lie in light stretched across billions of years, distorted, weakened, mixed with the noise of cosmic expansion. We are trying to reconstruct an ancient language from fragments and whispers. But the galaxies JWST has revealed, so massive, so bright, so early, are like bold signatures at the bottom of a torn page. Their existence declares that something happened. Something we did not predict. Something our current physics cannot explain. The possibility lingers like a shadow. Perhaps we have mistaken the surface of reality for its depth. Perhaps the universe still hides forces or symmetries that we have yet to uncover. Perhaps the early cosmos was a place where matter, energy, and spacetime interacted in ways our equations cannot yet describe. And beneath all these questions lies the one that gnaws at the edges of every physicist's mind. If the physics we know is only part of the story, what else lies beneath the surface of reality, waiting to be discovered? Redshift is supposed to be a cosmic clock, simple, elegant, reliable. It tells us how far away something is, how fast space is expanding, and, most importantly, how old the light truly is. It is the ruler by which cosmologists measure the universe's deepest history. But when JWST captured galaxies with redshifts so extreme they bordered on the impossible, that ruler began to tremble. Suddenly, the one measurement we trusted most came into question. Because if redshift is misleading us, then everything we think we know about the early universe, the timeline, the structure, the formation of stars, is built on sand. To understand why this is so destabilizing, imagine watching a storm through a warped window. The shapes you see may look violent or calm, close or far away, but the warping changes everything. Now imagine the entire universe being observed through such a window, except the warping is created not by glass, but by space itself, gravity bending light, dust reddening it, cosmic expansion stretching it. Redshift becomes a translation, and translations can distort the message. The earliest galaxies JWST observed displayed redshifts so high they placed them within the universe's first 200 million years, a period too early for structures of their size and maturity to exist. But some astronomers wondered if the redshift readings could be deceiving us. Perhaps these galaxies were not as ancient as they appeared. Perhaps their light was altered in subtle, unexpected ways long before it reached JWST's golden mirrors. One possibility lies in dust. Cosmic dust absorbs blue light and allows red light to pass through, effectively reddening the signal. If a galaxy contains an unusual amount of early dust, and some appear to, its light could mimic the signature of extreme redshift. But dust alone cannot explain galaxies that should not exist. Dust can disguise temperature, brightness, even composition, but not mass on this scale. The mystery goes deeper. Another possibility involves the chaotic environments of the early universe. Gravity from nearby galaxies, dark matter halos, and dense gas could have distorted the path of light. When light travels through such turbulent regions, it can be stretched, bent, or magnified in ways that imitate high redshift. A galaxy might appear more distant or older than it truly is. But these effects are usually small, localized, and well understood. The anomalies JWST found are far too widespread for such simple distortions to account for. The next suspect is gravitational redshift. Light climbing out of a massive gravitational well loses energy, shifting into redder wavelengths. If the early galaxies housed enormous black holes or dense star clusters, their light might be significantly reddened before it ever touched intergalactic space. This could trick our instruments into interpreting a younger galaxy as primordial. And indeed, some of the earliest galaxies JWST saw appeared to have suspiciously bright cores, possible signs of early black holes. But this explanation, too, has limits. Gravitational redshift would only affect the central regions, not entire galactic structures. The broad redshift signatures JWST measured cannot easily be explained away. Some physicists began to suspect a deeper issue. The way we calculate redshift might break down under extreme conditions. The universe expands, stretching light along with it. But what if that expansion was not uniform? What if the early cosmos expanded in pulses, waves, or uneven bursts? Light emitted during turbulent expansion could be stretched in inconsistent ways, producing artificially high redshifts. Imagine a runner sprinting on a treadmill that changes speed without warning. The runner's movement becomes impossible to measure accurately unless the treadmill's rhythm is understood. The early universe may have had no rhythm, only chaos. Another unsettling theory proposes that the very fabric of spacetime might alter light differently at high energies. In the earliest moments after the Big Bang, spacetime could have been more flexible, more fluid, more easily warped. Light traveling through such a medium could stretch disproportionately, exaggerating its redshift. Under this scenario, extreme redshift might not correspond to extreme distance or extreme age. It could be a side effect of primordial spacetime behaving in ways that modern physics cannot yet simulate. Then there is the possibility that light itself may not be the constant storyteller we assume. In extreme environments, photons can interact with fields or particles in exotic ways. Some theories suggest that in the early universe, interactions between light and dark matter or stray quantum fields could subtly modify wavelengths. The effect would be tiny under normal conditions, but enormous across billions of years. If even a fraction of a % shift occurs at the source, cosmologists could misinterpret a galaxy's age by hundreds of millions of years. The most radical idea, however, lurks at the edges of theoretical physics. Perhaps redshift does not measure what we think it measures at the universe's extreme limits. The rules that define redshift today were built from observations of mature galaxies, stable stars, and calm regions of spacetime. But the early universe was none of these things. It was wild, violent, superheated, unstable. If the relationship between redshift and distance changes in the earliest epochs, then every timeline in cosmology, every chart, simulation, and history book is fundamentally flawed. Yet even as scientists probe these possibilities, a troubling realization remains. No simple redshift distortion can fully explain the existence of galaxies that seem far too massive, structured, and chemically evolved for their supposed age. Even if redshift is partly misleading us, it cannot conjure heavy elements where none should exist, cannot produce complex galactic rotation from chaos. It cannot create mature star populations in a universe that should still be forming its first clusters. Redshift might be lying, but only a little. The deeper truth lies somewhere beneath. Astronomers now stand at a crossroads. To trust the redshift data is to accept that the early universe behaved in ways that violate known physics. To distrust the redshift data is to accept that our tools for measuring cosmic history may crumble at the edges of reality. Either choice leads to the same conclusion. Something about the universe's first moments is fundamentally wrong in our current understanding. The redshift puzzle is more than a technical debate. It is a crack in the cosmic map, a whisper that the universe still hides secrets behind the very light that reveals it. And with each new observation, the question grows sharper, more insistent, impossible to ignore. If redshift cannot be fully trusted at the edge of time, then what truly lies at the universe's beginning, and how much of what we believe is an illusion painted by stretched light? For more than a century, light has been our most faithful messenger, carrying whispers from distant galaxies across the gulf of space. It has told us where stars are born, where they die, how the cosmos expands, and how gravity bends the fabric of reality. But sometimes, even the most loyal messenger can mislead, not out of deceit, but because the path it travels is unforgiving. In the deepest reaches of the universe, where gravity twists like a serpent and space-time folds like molten metal, light can be distorted, stretched, magnified, and rearranged. It can paint illusions onto the cosmic canvas, tricking our eyes into seeing what isn't truly there. This is the dangerous power of gravitational lensing, cosmic mirages sculpted by mass so overwhelming that it bends the trajectory of time itself. When JWST captured images of ancient galaxies shining brighter, sharper, and more numerous than expected, one of the first explanations scientists considered was lensing. Perhaps these galaxies were not as large or as early as they appeared. Perhaps their light had been magnified by invisible masses lying between us and them, clusters of dark matter or faint galaxies stretching and amplifying the light like curved glass. If that were true, then JWST wasn't showing us the earliest universe directly. It was showing us a reflection, a distortion, a cosmic sleight of hand. But the possibility of such a giant cosmic mirage is far from simple. To imagine gravitational lensing, picture a vast, transparent sphere placed between you and a distant candle flame. The candle's light bends through the sphere, making it appear stretched, multiplied, or even brighter than it truly is. On a cosmic scale, the sphere is massive galaxies, dark matter halos, or even entire clusters. Their gravity warps the fabric of spacetime, forcing light to take curved paths. Sometimes the light splits into arcs, rings, or mirrored images. Other times, it focuses into a single point, amplifying distant objects that would otherwise be invisible. JWST's deep-field images revealed tiny, bright specks, galaxies so small and distant they should have been too faint to see. The simplest explanation was lensing. Mass somewhere in the foreground must have magnified them. But when astronomers searched for the lensing structures, many were missing. There were no massive clusters, no dense galaxies, no obvious foreground masses strong enough to produce the level of magnification needed. It was as if the universe had created impossible clarity without the usual distortions. And yet, lensing still whispered its presence in subtle ways. Some galaxies appeared stretched, not chaotically, but in smooth arcs, the telltale signature of gravitational bending. Others had unusual shapes, elongated or smeared across space. These distortions suggested that invisible mass, dark matter, was warping the light. If dark matter halos existed in just the right places, they could create faint lensing effects without being easily detectable. This possibility opened a deeper mystery. Could the early universe have had more concentrated dark matter structures than we thought? Structures dense enough to bend light but too faint to be seen directly? If so, then JWST's images might be showing us a hall of mirrors, where galaxies appear duplicated or magnified or misplaced, not because they are extraordinary, but because we are seeing them through distorted spacetime. One particularly perplexing observation involved galaxies that appeared enormously bright for their size. Their luminosity suggested impossible star formation rates, thousands of suns igniting every year in galaxies no larger than common dwarfs. But if lensing magnified their light, then perhaps these galaxies were normal-sized, simply stretched across the cosmic stage. The issue was not their nature, but their apparent exaggeration. But there was a complication. Gravitational lensing typically produces recognizable artifacts, arcs, rings, repeated patterns. JWST did observe such features in some fields, but not nearly enough to account for hundreds of galaxies appearing brighter and older than they should. The scale of the anomaly far exceeded what typical lensing could explain. Scientists began exploring a more exotic possibility: microlensing and millilensing, distortions caused not by massive structures, but by small clumps of dark matter, rogue black holes, or even primordial black holes formed in the first milliseconds after the Big Bang. These tiny gravitational lenses can magnify distant objects subtly, without creating large arcs or rings. If the early universe was filled with dense pockets of such objects, they could collectively distort the light passing through them, making distant galaxies seem older or brighter. This idea, though intriguing, opened a darker implication. What if the early universe was filled with these objects because it was far more chaotic than we imagined? What if the smooth cosmic web we see today was preceded by a violent era of collapses and fragmentations that left behind an ocean of small gravitational lenses, now invisible but still affecting ancient light? Then came another possibility, one that pushed scientists into deeply unsettling territory. Perhaps the missing lenses weren't missing at all. Perhaps they were too dim to detect because they were made almost entirely of dark matter. A dark matter galaxy, without stars, would bend light just as effectively as a visible galaxy but leave no luminous trace. If such objects existed in great numbers, the universe might be filled with invisible lenses, distorting the light from early galaxies like ripples in glass. Under this model, the cosmos becomes a labyrinth of invisible structures. Light doesn't travel straight. It weaves its way between dark matter concentrations, taking detours, looping around unseen masses, arriving reshaped at our detectors. What we interpret as ancient galaxies may be partly illusions, magnified, duplicated, or compressed by a universe whose true architecture we cannot see. Yet even lensing, micro, milli, or massive, cannot fully erase the mystery. Lensing can make galaxies appear brighter, bigger, or distorted, but it cannot create heavy elements where none should exist. It cannot generate mature star populations in a universe too young to support them. It cannot produce rotational patterns requiring hundreds of millions of years. At best, lensing explains how galaxies appear, cannot explain what they are. And so we face a paradox. Perhaps some of what JWST sees is a mirage, but the light behind the mirage still carries secrets that lensing cannot disguise. Lensing may soften the edges of the mystery, but it does not erase its core. Instead, it reveals something deeper. The early universe was a warped hall of mirrors, filled with unseen masses bending its first light into shapes that challenge our understanding. And as we peer through these distortions, one question grows sharper, echoing across the cosmic void. If we are seeing the universe through a maze of gravitational illusions, then how much of what we call the beginning is real, and how much is only the shadow cast by something we cannot yet see? For decades, scientists have trusted simulations to be their glimpses into the universe's past and future. Vast digital universes built on supercomputers, worlds governed by the laws of physics we believe to be true. In these simulations, galaxies grow slowly, starting as fragile clouds of gas, gradually gathering mass, merging, collapsing, and dispersing. Stars form in tiny pockets. Dark matter creates a gentle web, pulling everything into place like invisible hands weaving a tapestry. It is all neat, predictable, elegant. But when JWST opened its eyes and looked into the real depths of cosmic history, it showed us something else entirely. The universe it revealed is not like the one inside our machines. It is faster, brighter, denser, more chaotic, more alive. And for the first time, simulations do not match reality. Imagine standing before a painting you have studied your entire life, one you believed you knew every brushstroke of. Then someone shines a brighter light on it, revealing colors you never saw, shapes that contradict your memory, entire sections that seem alien. That is what JWST did to the universe we thought we understood. It exposed differences so deep that they now threaten the frameworks of modern cosmology. In simulations, the early universe is dark and slow. The first few 100 million years are dominated by small halos of dark matter pulling gas inward. The clouds must cool before they can ignite stars, and this cooling takes extraordinary time. When stars finally form, they are sparse. Their galaxies are tiny, chaotic puddles of light, more smudges than structures. Over the next few billion years, galaxies merge and grow, forming spirals, ellipticals, and clusters. This is the narrative of cosmic evolution according to every credible model. But JWST looked back to the period when simulations predicted dark emptiness, and instead found luminous cities in the night. The first blow came when JWST revealed galaxies with masses comparable to the Milky Way far earlier than any simulation allows. No known model can produce so much mass so quickly. These galaxies seem to defy the cooling times of gas, the gradual buildup of dark matter, and even the maximum speed of star formation. In some simulations, even if you push parameters to their extremes, super-efficient cooling, hyperactive star formation, enormous early halos, you still cannot generate galaxies like the ones JWST captured. It was as if the universe skipped steps, leaping directly from primordial chaos into structured order with barely any intermediate stages. The next shock came from the brightness of early galaxies. Many of them shine with an intensity that defies every prediction. They produce stars at rates simulations cannot replicate without breaking the known laws of physics. The real universe, JWST suggests, created stars in the early epoch at a pace that our models deem impossible. This discrepancy raises a disturbing question. What if the rules governing star formation were different back then? What if conditions in the early cosmos allowed a kind of hyper-efficient conversion of gas into stars, a mode of creation that no simulation has ever accounted for? If that is true, then our models are missing a fundamental ingredient. But simulations do not only struggle with brightness and mass. They also fail to predict the structure of early galaxies. JWST found some galaxies that appear surprisingly smooth, rotationally supported, and orderly. They are not the chaotic, lumpy blobs simulations predict for such early times. Instead, they resemble miniature versions of mature galaxies, complete with organized movement and coherent shapes. How could such stability arise so quickly? What force shaped these systems with such elegance before cosmic turbulence had calmed? Some researchers attempted to modify simulations, tweaking dark matter properties, increasing gas densities, adjusting cooling functions. Yet, even the most extreme adjustments cannot replicate the JWST galaxies across the board. Fix one anomaly and another expands. The simulations begin to look like patchwork solutions, fragile fixes that hide deeper inconsistencies. The most haunting idea is that simulations cannot match the early universe because they are built on incomplete physics. Supercomputers run equations based on what we know: gravity, radiation, dark matter, gas dynamics. But what if the early universe operated under physical laws we have not yet discovered? What if unknown forces, unknown particles, or unknown interactions shaped those early galaxies? If so, no simulation, no matter how advanced, can recreate the truth until we uncover those missing pieces. Even dark matter itself becomes a suspect. In simulations, dark matter behaves like a cold, collisionless fluid, forming smooth halos. But what if early dark matter was different? More clumpy, more dynamic, more interactive. If dark matter in the early universe condensed faster or behaved turbulently, it could generate the deep gravitational wells needed to form massive galaxies quickly. But current simulations do not allow for such behavior because we do not know how to simulate something we cannot yet imagine. Then there is the question of feedback. the energy released by stars and black holes that regulates galaxy growth. In simulations, feedback slows formation, blowing gas outward and preventing runaway starbursts. Yet JWST's galaxies appear to have grown with extraordinary efficiency, unrestrained by the feedback that should have stopped them. This suggests that feedback might have worked differently, or that early galaxies somehow bypassed these limiting forces. Once again, simulations fail because they reflect a universe governed by rules that may not have existed at the beginning. Some scientists have suggested creating entirely new kinds of simulations, ones that allow for variable physical laws, exotic dark matter, altered constants, or unknown interactions. But these new simulations raise philosophical questions. If we must rewrite the rules to match JWST's observations, then what does that say about our theories? Were they always incomplete? Were they built on assumptions that now crumble under the weight of real data? Perhaps the most unsettling possibility is that simulations never showed us the universe as it was, but only the universe as we imagined it to be. They were constrained by human assumptions, human limitations, human expectations. JWST broke those assumptions open. It showed us that the cosmic story is not one of slow, orderly growth, but of rapid, explosive creativity. A universe that built itself with urgency, as if racing against time. The rift between simulations and reality is more than a scientific problem. It is a narrative crisis. The universe we thought we understood is no longer the universe we see. The digital cosmos inside our machines is neat, predictable, and reasonable. The real cosmos is wild, fast, and impossibly bold. As scientists attempt to reconcile these contradictions, one truth becomes increasingly clear. Simulations are not wrong, they are incomplete. They are maps drawn with the information we had, not the information we needed. JWST has illuminated regions of cosmic history that simulations cannot yet reach, revealing the shadows where new physics may be hiding. And as this gap widens, a new question echoes through research centers around the world. If our simulations fail to recreate the universe's first moments, then what undiscovered truths shaped the cosmos long before theory ever caught up? In the beginning, when the universe was still trembling from its violent birth, when stars were only flickers of hope in a sea of darkness, something else may have emerged in the chaos. Something so dense, so hungry, so impossibly powerful that it could bend the early cosmos to its will. Black holes. Not the slow-growing monsters we see today at the hearts of galaxies, but ancient titans born almost instantly, rising out of the turbulence like cosmic predators. Their existence in the earliest chapters of the universe has long been debated, until JWST arrived and uncovered evidence that these primordial beasts might have been there from the start. When scientists first examined JWST's data, some galaxies showed signatures that defied explanation. Brilliant cores shining far too brightly for their size, light curves suggesting violent energy output, and dense central regions that could only be powered by something with immense gravitational pull. These were not the gentle glows of young star clusters. They were the blazing, ferocious signals of black holes, supermassive black holes, existing at a time when the universe was barely a toddler in cosmic terms. The implications were staggering. In modern galaxies, black holes grow slowly, feeding on gas and stars over billions of years. It takes the collapse of massive stars, the merging of stellar remnants, and relentless accretion for a black hole to reach millions or billions of solar masses. But the early universe did not have billions of years. It barely had millions. There should not have been enough time to build black holes large enough to power the intense brightness JWST observed. And yet, there they were, cosmic engines burning with impossible fury. To understand how shocking this is, imagine a city that appears fully grown overnight. Skyscrapers rising where there were no foundations, lights glowing before streets were built, systems functioning before anyone understood how they were created. That is what these black holes represent. They did not wait for galaxies to form. They may have formed first, dragging gas, dust, and matter around them, shaping the galaxies that now orbit their gravitational dominion. Some theorists have long suspected this possibility. Black holes might be the seeds, not the byproducts of galaxy formation. In this model, massive black holes act as gravitational anchors in the early universe, gathering material into spinning structures that later become galaxies. JWST's unexpected observations now lend weight to this once speculative idea, as several early galaxies appear to revolve around cores too massive and too energetic to be anything else. But the question remains, how did these black holes form so quickly? One possibility is the direct collapse model. Instead of forming from the remnants of stars, these black holes may have emerged directly from the collapse of enormous gas clouds. Clouds so dense and so vast that they bypass star formation entirely. In one catastrophic collapse, millions of solar masses could fall inward, forming a black hole in a cosmic instant. The universe was hotter then, denser, more chaotic. The conditions for such collapses may have been perfect, producing black holes of breathtaking scale before the first galaxies had even taken shape. Another idea takes us deeper into exotic physics. Perhaps the early universe, still rippling with intense energy fields, allowed black holes to grow far faster than they can today. Some researchers propose that the fundamental forces, gravity, electromagnetism, and the nuclear forces, may have behaved differently in the universe's infancy. If gravity was stronger, even slightly, it could have driven matter into black holes with terrifying efficiency, allowing them to balloon in mass at speeds unimaginable today. Yet another theory suggests the existence of primordial black holes, objects formed in the first fractions of a second after the Big Bang, before atoms, before light, before structure. These black holes could have emerged from density fluctuations in the early plasma, forming a population of compact objects scattered across the universe. Some might have evaporated. Others might have persisted. The largest could have grown into the ancient supermassive black holes now haunting JWST's observations. If even a few primordial black holes survived the earliest turbulence, they could have acted as seeds for galaxy formation, pulling material toward them with relentless hunger. This idea, once controversial, is receiving renewed attention. JWST's discoveries provide indirect evidence that black holes may have been present earlier than any conventional model allows. And if primordial black holes existed, they may also explain other cosmic mysteries, dark matter, early lensing anomalies, even the strange distribution of galaxies in the cosmic web. But black holes, despite their terrifying simplicity, also bring elegance to the puzzle. Their gravitational pull could accelerate the growth of early galaxies, giving them structure and mass at incredible pace. Their radiation could heat and ionize surrounding gas, triggering waves of star formation. Their violent feeding frenzies could sculpt the interstellar medium, shaping the young cosmos one eruption at a time. Imagine the early universe not as a calm dawn, but as a battlefield of collapsing clouds, exploding stars, and voracious black holes tearing through the dark. In this realm, galaxies are not delicately assembled, they are forged through violence. Black holes ignite star formation in some regions while extinguishing it in others. They drive winds that sculpt cosmic landscapes. They collide, merge, and reshape the gravitational foundations of everything nearby. This chaotic dance could have created the intense structures JWST sees, structures that should not exist according to modern theory. Yet even this explanation carries unsettling implications. If black holes were shaping the early universe so aggressively, then our entire understanding of cosmic evolution may be inverted. Instead of galaxies forming black holes may have created galaxies. Instead of star formation driving structure, black hole dynamics may have orchestrated the earliest cosmic architecture. The more JWST reveals, the more plausible this reversal seems. In some of the oldest galaxies detected, the black hole at the center appears disproportionately massive compared to the galaxies surrounding it, like a heart too big for its body. This imbalance is not seen in modern galaxies, where a predictable ratio exists between black hole mass and galactic mass. Something different was happening back then. Something wild. Something fast. And so the mystery deepens. Did black holes awaken at the very beginning, rising like titans from the primordial fog? Did they carve the universe into shape, binding the first galaxies with gravitational chains stronger than any star could forge? Or were they remnants of an even earlier, hidden era of the cosmos? An era we have yet to imagine? The light that JWST captured offers no clear answer. It only reveals the presence of giants at the dawn of time, giants that should not exist, yet do. And with every new observation, one question grows more haunting. If black holes were there at the beginning, shaping galaxies before galaxies existed, what else was lurking in the universe's first darkness, waiting to be discovered? Could it represent a localized pocket of spacetime stabilized amid chaos? Might it involve unknown energy fields or exotic particles? These possibilities deepen both the scientific inquiry and the narrative tension, offering viewers hooks that sustain engagement and fuel curiosity. Cinematic sequences emphasize this interplay. Tidal tails flare with bright gas, supernovae explode in bursts of light, and yet the anomaly pulses with a faint, mysterious glow, bridging the gap between chaos and subtlety. Scientific collaboration is essential to understanding the anomaly. Observatories worldwide coordinate observations, sharing data, cross-validating findings, and refining theoretical models. Multi-wavelength imaging captures the anomaly's behavior across different parts of the electromagnetic spectrum, while computational simulations test hypotheses against real-world data. Each new insight is incorporated into a growing framework of understanding, yet every discovery raises further questions, reinforcing the frontier nature of this investigation. Cinematically, the human element of collaboration adds depth. Scientists working together, comparing notes, hypothesizing and re-evaluating models, create a parallel narrative of human curiosity, perseverance, and ingenuity amidst the cosmic mystery. The anomaly challenges conventional models of galactic collision and evolution. Standard simulations predict the behavior of stars, gas clouds, and dark matter during such events. Yet the anomaly defies expectations. Its subtle influence, persistence, and irregular behavior suggest additional forces or phenomena may be at work. Forces or particles that have yet to be incorporated into existing physical theories. By resisting classification, the anomaly becomes both a puzzle and a catalyst for new theoretical development, inspiring scientists to explore uncharted areas of physics and cosmology. This narrative device reinforces engagement, drawing viewers into a story where every answer leads to further questions, and every observation hints at deeper cosmic truths. Emotionally, the anomaly captivates by combining subtlety with mystery. Amid the explosive backdrop of colliding galaxies, its faint glow evokes awe, curiosity, and wonder. Cinematic storytelling accentuates this effect. Stars are flung into arcs, gas clouds flare in vivid color, and supernovae punctuate the darkness. Yet the anomaly remains a quiet, luminous focal point, drawing attention through contrast. This interplay of visual spectacle and subtle mystery engages viewers on multiple levels, allowing them to experience both the grandeur of the universe and the profound intrigue of phenomena that resist comprehension. The anomaly becomes a symbol not only of cosmic mystery but of the enduring human pursuit of knowledge. Ultimately, the anomaly embodies the intersection of observation, theory, and imagination. It challenges understanding, inspires bold hypotheses, and compels both scientists and viewers to confront the unknown. Through careful observation, sophisticated modeling, and imaginative speculation, researchers strive to unravel its mysteries, while audiences share in the awe, curiosity, and intellectual engagement of exploration. Cinematically, the anomaly's faint glow persists amidst colliding galaxies, symbolizing humanity's relentless pursuit of knowledge, the complexity of the cosmos, and the profound mysteries that continue to inspire both science and imagination. By the conclusion of this section, viewers are fully immersed in the anomaly's enigma, aware that it is neither a simple phenomenon nor a static object, but a dynamic, evolving mystery that challenges our understanding of the universe and sets the stage for the deeper exploration in the subsequent sections. For as long as we have studied the cosmos, one number has shaped our entire understanding of existence. The age of the universe. 13.8 billion years. A figure etched into textbooks, whispered in documentaries, held up as one of science's greatest achievements. It is the anchor of cosmology, the foundation upon which timelines, models, and theories rest. But when JWST uncovered galaxies that appeared impossibly old, impossibly massive, impossibly evolved for their place in cosmic history, a quiet, unsettling possibility began to rise through the scientific community. What if the universe is older than it looks? What if our cosmic clock is off, not by minutes or hours, but by hundreds of millions, maybe even billions of years? It sounds unthinkable. The age of the universe is calculated from the cosmic microwave background, the afterglow of the Big Bang, a faint radiation field stretched across the whole sky. We've measured its temperature, studied its tiny fluctuations, and used them to reconstruct the expansion history of the cosmos. The numbers align beautifully with the physics we trust. But JWST's ancient galaxies don't fit that story. They are too evolved, too luminous, too chemically enriched to fit inside the narrow window allowed by a 13.8 billion-year universe. It's like finding fossils of complex life in rocks that should predate the formation of Earth. Something doesn't match. One idea, whispered cautiously at first, is that the universe might be older than the cosmic microwave background suggests. Maybe the Big Bang wasn't the beginning, just the beginning of the universe as we know it. Perhaps an earlier era existed before the CMB was released, a hidden epoch of which no trace remains except the galaxies that appear too old for their own good. If that is true, the universe could be far older. Its timeline stretched, its secrets buried beneath cycles of cosmic evolution we have yet to uncover. Another possibility challenges not the age of the universe itself, but the assumptions tied to its expansion. The rate at which the universe expands, known as the Hubble constant, has become one of the greatest tensions in modern physics. Two different methods produce two different values, a conflict known as the Hubble tension. JWST's early galaxies only deepen this conflict. Their properties imply rapid early formation that doesn't match either value. Some physicists began to wonder, if our measurements of expansion are distorted, could our interpretation of cosmic age be distorted too? Imagine trying to judge the age of a tree based solely on its height, unaware that the tree grew faster in its early years due to an unknown nutrient in the soil. You would underestimate its true age. Similarly, if the universe expanded unevenly, speeding up, slowing down, then speeding up again, we could be misjudging how long it has truly been unfolding. Some models propose precisely this, variable expansion rates that change over cosmic history. If the early universe expanded more slowly than assumed, then the timeline stretches naturally. The first stars and galaxies would have had more time to grow and evolve before the light we now see began its journey toward us. Under this model, the universe may still be 13.8 billion years old from the last big expansion phase, but the structures within it may have roots extending deeper into time than the CMB alone can reveal. Still, stranger theories suggest that dark energy, the mysterious force accelerating cosmic expansion, might have behaved differently in the past. If dark energy fluctuated or even reversed temporarily, the universe could have experienced a pause, a moment where the cosmic clock slowed. During this pause, galaxies could evolve significantly while gaining little additional redshift. To us, observing billions of years later, these galaxies would appear too mature for their redshift value, creating the illusion of an older universe. Then there are the truly bold ideas, those that venture into realms where cosmology brushes against philosophy. Some propose that the universe may have undergone multiple cycles, expansions and contractions, each resetting the cosmic landscape. Under cyclic models, the Big Bang is not the beginning but a rebirth, a moment when the previous universe collapsed into a singularity and exploded outward again. If remnants or signatures from a previous cycle survive the transition, embedded in early galaxies or black holes, they could carry the illusion of ancient age, making them appear older than the current cycle allows. There is even a theory suggesting that time itself may not have a fixed zero point. In such a framework, the early universe might not have had a clear beginning. Instead, it emerged gradually from a quantum haze, with time crystallizing slowly out of a timeless state. If so, age becomes a blurry concept during the first phases, and any structure forming during that transitional period would appear impossibly ancient by the time-stable, measurable time began. These ideas are not embraced easily. They threaten the precision cosmology that scientists have spent decades building. They challenge the notion that the universe is simple, measurable, predictable. They force us to re-examine our most trusted tools. But JWST's data sits in silence, refusing to be dismissed. Some of the earliest galaxies show chemical fingerprints, elements like oxygen, nitrogen, and carbon, that require multiple generations of stars to produce. This alone implies a history longer than the standard timeline allows. Other galaxies show signs of large-scale organization, rotation curves, disk structures, gravitational equilibrium. These features take time, real time, to emerge. They cannot be rushed. They cannot be faked. So what is the universe trying to tell us? Perhaps the cosmos is older than we think. Not older in raw numbers, but older in experience. It may have lived through phases we cannot see, eras erased by expansion or hidden behind quantum boundaries. Its timeline may be stretched, folded, or fractured in ways we do not yet understand. Or perhaps our method of measuring time, our cosmic calendar, is incomplete. Redshift, cooling rates, star ages, expansion speeds, all rely on assumptions that may be subtly wrong. The early universe may have lived under physical laws that distort those measurements, creating the illusion of ancientness where none exists. Either way, a shadow has fallen across the age of the universe. A shadow cast not by doubt, but by discovery. JWST has shown us galaxies that should not be possible within a 13.8 billion-year timeline. And if those galaxies are real, and they are, then the question becomes inescapable. Is the universe older than it appears, or have we misunderstood the very meaning of age itself? The answer lies buried in the first light of creation. A light now reaching us, carrying stories that challenge everything we thought we knew about time, history, and the true age of the cosmos. For decades, cosmology has felt like a house built on bedrock, solid, unmoving, dependable. The equations fit. The models agreed. The universe behaved like a well-written script. Even its mysteries, dark matter, dark energy, inflation, felt like puzzles waiting to be solved, not threats to reality itself. But when JWST revealed galaxies that should not exist, galaxies too old, too massive, too structured for their place in time, that bedrock began to fracture. Quietly at first, then violently, and now, those fractures stretch across every part of modern cosmology like cracks in ancient stone. It is no longer a question of adjustment. It is a question of reconstruction. Because when reality doesn't add up, the error may not lie in the data. It may lie in the story we've been telling ourselves. The universe, once predictable, has become a riddle wrapped in contradictions. Massive galaxies appear at a time when the universe should still be cooling. Heavy elements show up long before there should have been enough stars to forge them. Black holes exist at sizes that defy the timeline required to build them. Dark matter seems too organized. Time seems too cooperative. Redshift seems too extreme. Every anomaly sits like a piece of a shattered mirror, each reflecting a different version of the universe, none of which match the one we thought we lived in. The contradiction is not small. It is foundational. Take the standard model of cosmology, the lambda-CDM framework. It tells us the universe started with a bang, expanded rapidly, cooled slowly, formed small structures first, and then gradually built larger ones. But JWST's galaxies are large first, mature first, bright first. They make lambda-CDM look less like a description of reality and more like a comforting story, crafted around limited observations from a time before we could see this far. The tension is palpable in scientific circles. Behind the formal discussions and cautious language, there is a sense of alarm, an awareness that the universe is not simply challenging our theories. It is mocking them. It is as if the cosmos has been whispering all along that we understood only the surface, not the depths. And now the whisper has become a roar. Some scientists suggest that the discrepancies can be explained by tweaking parameters, adjusting star formation rates, modifying dark matter distributions, revising cooling times. But these tweaks feel like patching holes in a sinking ship. Each fix solves one problem but worsens another. Increase star formation efficiency, and you break chemical evolution models. Boost dark matter collapse, and you violate structure formation rules. Change feedback rates, and galaxies become too bright, too early, but lose stability later. Every adjustment exposes a deeper inconsistency. It is as though the universe is refusing to be boxed into our equations. Others propose that we may be interpreting the data incorrectly. Maybe redshift distances are slightly wrong. Maybe lensing tricks us. Maybe early dust alters the signals. But these explanations crumble under scrutiny. They cannot account for all the anomalies. Not the masses, not the chemical signatures, not the rotation curves, not the gravitational behavior. Even if every illusion were peeled back, the core impossibility remains. The galaxies are there. They are real. And they should not be. This realization has ignited an intellectual crisis unlike anything cosmology has faced in a century. Not since Einstein upended Newton, not since Hubble revealed expanding space, has the universe forced such a dramatic reevaluation. The tension between excitement and dread is almost tangible, like standing on the edge of a cliff overlooking a fog-shrouded abyss. Something is down there, some deeper truth, but stepping forward means abandoning the safety of everything we thought we understood. Conversations among researchers have taken on a tone that borders on existential. If our entire cosmic timeline is wrong, then what else is wrong? If the early universe behaved differently than our models predict, what does that say about the nature of reality? If black holes, galaxies, and stars formed in ways we never imagined, what unseen forces or hidden processes were at work? The contradictions pile up until they stop being contradictions and start looking like clues. Perhaps the early universe was governed by physics we have not yet discovered. Perhaps dark matter behaved differently. Perhaps time flowed differently. Perhaps inflation seeded strange structures. Perhaps gravity acted with unfamiliar strength. Or perhaps the universe carries scars from an era that came before the Big Bang. Scars reflected in the galaxy's JWST is now revealing. Each possibility is bold. Each one demands a transformation of cosmology. And yet, refusing these possibilities means refusing the evidence itself. In research centers around the world, theorists rewrite equations late into the night, crossing out assumptions previously considered untouchable. Simulation teams push their models into regimes they once thought impossible, hoping to reproduce what JWST sees but failing again and again. Observational astronomers triple-check their measurements, hoping the instruments made a mistake. But the instruments are flawless. The universe is the one misbehaving. And so, a shift begins, not sudden but inevitable. A shift from patching theories to reimagining them. A shift from explaining anomalies to embracing them. A shift from defending the old model to searching for a new one. There is a strange beauty in this crisis. A sense of awakening. When reality no longer fits, it forces the mind to expand. It demands creativity, bravery, and humility. For the first time in decades, cosmology feels alive with mystery again, like the early days when every discovery was a revolution. We stand at the edge of a scientific horizon, watching the known universe dissolve into something deeper, stranger, more magnificent than our theories ever dared describe. The contradictions are no longer obstacles, they are signposts. They point toward a truth the universe has kept hidden until now. And as JWST continues its relentless gaze into the abyss of cosmic history, one question grows louder, echoing across laboratories, observatories, and theoretical frontiers alike. If reality doesn't add up, what new reality waits beyond our broken equations, waiting to be discovered? Revolutions never arrive gently. They emerge from tension, from fractures, from the slow accumulation of contradictions until the old world simply can't hold itself together anymore. That is where cosmology now stands, on the threshold of a scientific revolution its architects did not expect. The James Webb Space Telescope, with its golden mirrors and impossible clarity, has done more than observe the universe. It has destabilized it. It has shaken the pillars of cosmological theory so profoundly that the next era of science is beginning to take shape right before our eyes. And like all revolutions, this one will be defined not by chaos, but by imagination, by our willingness to rewrite the story of existence itself. The seeds of this revolution were planted long before JWST lifted off. They existed in the unexplained behaviors of dark matter, in the accelerating expansion of the universe, in the mismatch between Hubble constant measurements, in the odd alignments of cosmic structures, in the strange anomalies hiding in the cosmic microwave background, each one a whisper that something was amiss. But they were subtle, too subtle to force a reckoning. Scientists addressed them with careful adjustments, minor corrections, mathematical bandages meant to keep the old model intact. JWST did not offer whispers. It offered an eruption. Its images of ancient galaxies were like a spotlight shining into a room we thought we had mapped completely, revealing doors we didn't know existed, corridors winding into darkness. To meet these revelations head-on, cosmologists began opening themselves to something they've historically resisted: the possibility of new physics. Ideas once considered too strange, too speculative, too bold are now entering mainstream discussion. And the scientific revolution ahead will likely be forged from these very ideas. One of the first areas poised for transformation is dark matter theory. For decades, dark matter has been treated as cold, slow, passive, interacting only through gravity. But JWST's galaxies suggest a universe where structures formed too quickly for such a passive, hands-off substance to suffice. In response, theorists are now exploring variations: warm dark matter, self-interacting dark matter that clumps or cools, dark matter that fragments into exotic forms. Some models propose dark matter had multiple phases, like steam condensing into water, transitioning from one behavior to another. In the earliest epoch, it might have collapsed rapidly, forming deep gravitational wells that nurtured early galaxies in ways our current models cannot replicate. The revolution may also extend to gravity itself. For the first time since Einstein, credible researchers are questioning whether the equations governing gravity are complete. Modified gravity theories, once tucked away in the margins of cosmological debate, are now being re-examined with urgency. Maybe gravity behaved differently in the early universe, acting with greater strength or under altered rules. Maybe gravitational collapse was more efficient when the universe was young. These possibilities, once fringe, now carry a weight they never had before. JWST's observations have reopened the door to a new gravitational paradigm. Then there is inflation, the explosive expansion at the universe's birth. For years, it seemed untouchable, a near-perfect explanation for the uniformity of the cosmos. But JWST hints that early structure formation may have been seeded by more chaotic or uneven inflation than we imagined. This has triggered fresh interest in multi-field inflation, staggered inflation, stop-and-start inflation, or inflation driven by exotic quantum effects. Some of the most daring theories propose that inflation produced pockets of dense spacetime, cosmic seeds, that later blossomed into massive early galaxies. If even a fraction of these ideas prove correct, inflation will be rewritten from the ground up. But perhaps the most profound shift comes from the possibility that time itself may have behaved differently at the universe's dawn. If early time flowed at a different rate, if it stretched or contracted unpredictably, if it transitioned gradually into the stable flow we experience now, then every timeline in cosmology must be recalculated. The universe may have had more time for early galaxies to grow than we think. Not because it is older, but because time itself was elastic. This idea, once philosophical, is now a serious contender for scientific exploration. Yet revolutions do not thrive on equations alone. They emerge from the minds willing to imagine beyond accepted boundaries. And JWST has ignited that imagination. Young researchers entering the field today do so at a moment of extraordinary intellectual freedom. Old constraints are dissolving. Theories previously dismissed as speculative are receiving fresh attention. Questions once considered too strange. What if the universe had previous cycles? What if dark matter interacts with time? What if black holes formed before stars? Are now being asked openly. This revolution will not be confined to theory. It will drive new technologies, new missions, new experiments designed to probe the early universe with unprecedented precision. Future telescopes, both space-based and ground-based, will build on JWST's legacy. Instruments capable of detecting primordial black holes, exotic particles, or early gravitational effects will become priorities. Simulations will evolve too, incorporating physics that extend beyond the cold simplicity of lambda CDM. They will attempt to recreate universes with different constants, different forces, different flows of time. Some will fail spectacularly. Others will produce results that match the galaxies JWST revealed. And when that happens, the revolution will not just be theoretical, it will be verified. But revolutions also have emotional weight. Cosmology is not merely numbers and charts. It is humanity's attempt to tell the story of where everything came from. When that story changes, it changes us. The shift happening now carries the same awe felt when ancient astronomers first realized Earth was not the center of the universe. When Newton revealed that the heavens followed mathematical laws. When Hubble discovered the expansion of space. When Einstein bent spacetime with equations that defied intuition. These were not simply scientific moments. They were human moments, moments when the universe revealed a deeper layer of its truth. Now it is happening again. As JWST continues to peer deeper, more discoveries are inevitable. Some will confirm suspicions. Others will completely reshape the landscape again. The revolution will unfold not in a single burst but in waves, each wave rewriting part of the cosmic script. In the end, the coming scientific revolution may not simply correct our model of the universe. It may transform our understanding of reality itself. The early cosmos seems to defy the rules we take for granted. By uncovering that defiance, JWST has given us the most precious gift in science. A mystery too large to ignore, too compelling to dismiss, and too transformative to resist. And as the future dawns on this new era of discovery, one question echoes across observatories, across laboratories, across the quiet midnight desks of theorists rewriting the universe from scratch. If this is only the beginning of what JWST will reveal, how much stranger, deeper, and more astonishing will the universe become when the next revolution arrives? When JWST first opened its golden mirrors to the darkness, no one expected the universe to speak so boldly. Yet, in its very first observations, light from the edge of time spilled into our instruments like a forgotten truth finally returning home. Those early galaxies, too bright, too massive, too evolved, rose out of the void like ancient ghosts, challenging everything we believed about the universe's beginnings. They were not quiet relics. They were declarations. With every image, the universe revealed a secret that had been hidden behind dust, distortion, and the limits of our old telescopes. The early cosmos was not gentle or patient. It was a storm of creation. Stars igniting like firebursts, galaxies assembling with impossible speed, black holes awakening before physics allowed them to exist. JWST showed us a world that formed itself with urgency, as if racing against time itself. Those first secrets did more than rewrite our theories. They changed our relationship with the cosmos. The universe was no longer a distant story we thought we understood. It became a living mystery, dynamic, unpredictable, full of hidden chapters still waiting in the dark. Every anomaly JWST uncovered was not a mistake but a message. The universe is deeper, stranger, and more alive than we imagined. And even now, as the telescope continues to stare into the abyss, we know this is only the beginning. The light we've captured is just the first layer. Behind it lie the first stars, the first black holes, the first structures that shaped everything. JWST has cracked open the door, revealing only a sliver of what the cosmos holds. The secrets it has shown us are not conclusions. They are invitations to go further. There are moments when discovery does not bring closure but opens a wider doorway, revealing that the journey is far from over. That is where humanity now stands. After everything JWST has uncovered, the impossible galaxies, the ancient light, the contradictions woven into the first moments of time, we find ourselves at the edge of something vast, something unfinished. Instead of answers, the universe has given us an invitation. The earliest galaxies JWST revealed were never meant to solve the mystery of the cosmos. They were meant to show us that the mystery is larger than we ever imagined. Those bright, ancient structures are like sparks thrown from a hidden fire, hints of processes and eras we do not yet understand. They remind us that the universe did not unfold slowly or predictably. It erupted into existence with urgency, shaping stars, black holes, and galaxies at a pace that defies our theories. And now, standing before these revelations, we feel the shape of a deeper truth. The unknown is not shrinking. It is expanding. Scientists across the world now look at the sky with a renewed sense of wonder. Old models buckle under the weight of new data. New theories whisper from the edges of possibility. Even the most established ideas, time, gravity, cosmic evolution, feel less like certainties and more like questions waiting to be rewritten. JWST has not broken science. It has reignited it. Each deep-field image, each spectrum, each strange anomaly is a message from a universe that is still speaking. And what it says is simple: keep going. There is more to see, more to understand, more to question. The first secrets have been revealed, but they are only the opening chapter. The rest of the universe is still waiting in the dark, calling to us through the oldest light we have ever seen.